covered the Lewis relation and the Lewis relation with respect, and then gone over an adiabatic saturation of a cooling tower. From this example right here, we'll be deriving three separate derivatives that will give us position, the change in the temperature of the water with respect to position, and the change in temperature of the gas with respect to position. Now, once we have completed deriving these differential equations, we will go into Python and we'll solve for these differential equations with our given parameters that I gave at the beginning of the video, or at the beginning of part 1 of this video. Now, to start this part of the problem, we need to explain what is going on. Now, the cooling water at the top of the column is equal, or the height of the top of the column is equal to 0. And Z will be increasing as it goes down the cooling tower. The cooling tower is also packed with a certain type of material or a specific area of packing, which is meters squared per meters cubed. And then we also have a stream of water going down the cooling tower, and then we have a stream of gas that is going up the cooling tower. Now, both of these flow rates are in kilograms per meter second squared, and then we have our flow rate right here of the liquid, which is in kilograms per second. And then we have a gas flow rate right here, which is kilograms per meter squared second. I just said that. And then with this, we're going to start deriving our differential equations. Now, to start with our differential equations, we need to determine what is going on for the in the molecular or the molar fraction of the gas flow rate. So we want to start with the change in the gas flow rate over the molecular fraction, or the molecular weight of water. Now, molecular weight of water is in moles, or the gas flow rate in this instance right here, or this part of the equation right here, is equal to mole seconds. Now, when we start thinking about this, we know that this equation will give us what is occurring in this equation is a mass transfer. So we need to apply a mass transfer coefficient, and we need to, we know that the change in the molecular fraction will change in consistency, so there will be a change in concentration with respect to the surface of the film of the gas going through the liquid. So we have the concentration of the gas at the surface, the gas away from the surface, and then we know we need to account for the specific area because this is going through a packing material. So we have the specific area times the, we have specific area by the specific volume. To get the specific volume, we need the cross-sectional area, which is A, times the height, which we defined as ET. Now, since this gas flow rate is moving upwards and we have our Z direction going in the opposite direction, we need to determine in which direction the gas flow rate is going. So we know that this equation will be negative. Now, this is our first problem. Now we need to actually get this within terms that we know. So we're going to change our concentrations with respect to the partial pressure. So we have I'm going to move, the DT, or the gas flow rate over the molecular weight is the mole fraction, so I'll change that to dy, and I'm going to move over the dt just so it's easier for us. Now we're going to change the concentrations to partial pressures. So we know that the partial pressure at the surface will be the partial pressure saturated by the liquid. So we'll say water at temperature TW over the gas constant times the temperature. And then we're going to subtract this from the mole fraction of water times the total pressure over the gas constant times the temperature. And then again, we need to equate this need to account for the packing material and the movement of the molecular weight and the gas flow rate. Now this whole term right here, if we remember back to the beginning of this class, we know that this part of the equation right here is actually the molar flux. So we know we want to simplify this problem. So we have the change in the mole fraction over the change in position is equal to the specific area times the molecular weight over the gas flow rate times the molar flux. So next we're going to, that is our first differential equation for the molar fraction with respect to position. Now that we've finished the first differential equation, we're going to move on to the second differential equation. The second differential equation is the change in temperature of the water with respect to position within the cooling tower. Now, when we think of the change in temperature, your head should immediately go to the change in enthalpy. So I'm going to first start by writing this equation as the change in enthalpy of water is equal to, we want to account for the liquid flow rate, which we had previously talked about. I believe it is in kilograms per second. And then we have the heat capacity, because we are going to have a change in temperature, which we are trying to find. So we will have a heat capacity because the change in temperature. And then we want to solve for the actual change in temperature. Now this is all flowing through a specific area, so we want to account for that cross-sectional area. Now when we're thinking about this, we also need to account for the evaporation that will occur. So when we write this out and simplify it, we have the heat transfer is equal to the temperature of the surface minus the temperature away from the surface, or we could say water is equal to the specific area times this cross-sectional area times the height, that should be height, which makes up for the specific volume that we need to solve for. Now, when we are talking about this, I had previously said we need to account for the evaporation of the water. So when we're thinking about evaporation, you need to have the heat of evaporation. And then you're going to, when you have a heat of evaporation within a differential equation, you also want to think of the molar flux, because there will be a change in diffusion within the gradation of the temperature of the water. So we have the molar flux, and then you also want to account for area in which the packing, the gradient is going to change. So again, we multiply it by the specific area times the cross-sectional area times the height. Now we want to account for the direction in which the this flow is for the molar flux. Now, because the gas is going from the bottom of the cooling tower to the top of the cooling tower, that is in the opposite direction of our preset Z direction. So we need to account for that by putting a negative sign there. Now, we want to simplify our equation, and we can quickly see by moving the change in temperature, which, this equation is equal to, you can have the change in the temperature of the water over the change in position of the cooling tower is equal to the cross-section, or the specific area divided by the liquid flow rate times the heat capacity of the liquid times the heat transfer times the change in the temperature of the gas minus the change in the temperature of the water minus the heat of evaporation and the molar flux of the water. Let me clean that up. Now this is our first equation. Now we need to go on to our third equation. Now our third equation, we're going to think of it sort of like looking at a specific area in a system, like we did for our previous problem on the adiabatic saturation. So we're going to be looking at a specific area within the cooling tower, and we have the change in enthalpy of the water going down, and we have the change in enthalpy of the gas going up through a specific area or volume, specific volume in which it is flowing. Now, for brevity, we're going to say that this is a steady state function. So we know that the enthalpy going in and the enthalpy going out will be the same. So when we look at the change in enthalpy, we'll have the change in the enthalpy of the water minus the change in enthalpy of the gas will all be equal to 0. When we see that, you quickly notice that the change in the enthalpy of the water is equal to the change in the enthalpy of the gas. So we know that we have the change in the enthalpy of the water here. Now we just need to put it in terms of the gas. So we're going to start off by saying the change in the enthalpy of the gas, is equal to the gas flow rate times the heat capacity of the gas times the temperature of the gas, all going through a specific area or cross-sectional area. And then you again need to account for the evaporation of the gas. So we have the heat of evaporation times the gas flow rate times the cross-sectional area divided by the molecular weight times the molar fraction. Now, we want to equate these two problems because, as we said, it is a steady state function. So we want to equate these two functions so that we can find our change in the temperature of the gas with respect to position. So we're going to write out, or I can copy and paste this equation right here. So I'm going to write out the equation as the change in the enthalpy of the gas, which we had previously just seen, plus the heat of evaporation times the gas flow rate cross-sectional area divided by the molecular weight times molar fraction, which is equal to the heat transfer, which will be the water in the liquid phase, times the change in temperature of the gas and the temperature, not change of temperature, but the temperature of the gas in the water at the cross-sectional area and the cross-sectional volume, which we need to account for right here with the specific volume. And then we account for the we account for the evaporation right here, going through that specific area. Can't write. Now we want to clean this up a little bit, and by just looking at this, we know that we can cancel out lambda G, or the heat of evaporation times gas flow rate divided by the the molecular weight, and heat of evaporation times the molar flux. Because we have previously derived these, they do cancel out. So we are left with the change in the temperature of the gas over, with respect to temperature, with respect to position, is equal to the cross-sectional area, cross-sectional surface area times the heat transfer coefficient divided by the gas flow rate times the heat capacity of the gas times the temperature of the gas at that location and the temperature of the water. Now this is our third and final differential equation. We're going to go on to Google Colab and work on Python to derive these within there, and then we'll plot out those with the given parameters that I had at the beginning of this video. So now we're on to the coding part of this exam. We are going to utilize the three differential equations that we just solved previously to solve for the change in the molar fraction with respect to position of the cooling tower, the change in the temperature of the water, and the change in the temperature of the gas with respect to position within the cooling tower. And then we are going to also plot these out so you can visually see that. So first, I added some tools in here for us to use. I have imported numpy as np, the numerical function for Python. I then put in, from plotly subplots to make subplots so that we can have our three graphs at the end of this video. I then imported plotly.io as PIO. Again, that's just for the graphs later on. I then had changed the background to be black, just looks a little bit nicer. And then I have utilized Python's tools of SciPy integrate to solve IVP for the initial variable problems that we'll be utilizing later on in this video to solve for our initial guesses for the derivatives. And then we'll be utilizing the root function that I got from SciPy optimized to actually solve for the these derivatives of the functions. So to begin this part, we need to pull some parameters that we were given at the beginning of the video. So I will be looking off a little to the side of the screen. I haven't memorized these numbers. So we are given the heat transfer coefficient to be equal to 10. Now that is in watts per meter squared. Next we have the gas constant, 3.14, and that's joules per mole Kelvin. And then next we want to get the density of the air, which is rho, and that's equal to 1.2, and that is kilograms per mole. Then we have, not mole, kilograms per meter squared. And then we have our heat capacity for air, which is equal to 1,000. That you can find online. for the heat capacity, kilograms per Kelvin. And then we need to find the heat capacity for water in the liquid phase and water in the gas phase. And again, these were are problems that you can find online, or not problems, these are values you can find online. Again, I'm just looking off computer. You have 4,190 for the heat capacity of water in the liquid phase, and then you have 40,700 for the heat capacity of water in the gas phase. Next, you want the heat transfer coefficient, which is heat transfer coefficient is equal to the heat transfer divided by the density of air times the heat capacity for air, and that gives us the heat heat transfer coefficient. Now again, I'm looking off screen. We're given that the packing, our specific volume for packing is A is equal to 5 meters squared per meters cubed. And then we were given the molecular weight of water. That was in kilograms, so you need to convert that from grams to kilograms. And we need the molecular weight for air, which is 29 e to the negative 3. That is, again, kilograms per mole. And then we want to put in our given velocity, which was given to us to be 5 meters squared. And then we want to have our liquid flow rate, which is equal to 0.5 times, or 0.5 not times, and then the units are kilograms per meter squared seconds. And then we are also given the pressure of the system to be 1,325 pascals. We want to enter the height of the cooling tower, which was 20 meters. And then we also want to put in the feed temperature for the water. And then we were given that to be 70 Celsius, so we need to convert that to Kelvin. And that is Celsius to Kelvin for temperature of the water feed. And then you need the gas, which was also given, or air, let's call it air, feed, and that was 3.15. Again, that's Celsius to Kelvin for gas phase. Now, we are going to want to graph this, so I'm going to put in some line of code for the equally spaced lines. That will be z is equal to np.wind space, and then we want to give it to start at 0, go up to the height of the cooling tower, and then we want 21 equally spaced values from 0 to 20. And then we should be all good on that. Oh, be nice if you spelled row right. So now we need to utilize Antoine's equation for the partial pressures. So we're going to define a function for the partial pressures at temperature T, and then we will be utilizing the Antoine's equation. So we want to return our value, and then I'm going to look up the Antoine's equation for the partial pressure of water, which looks like it's 10 raised to the 8.0131 minus 1730.63 divided by 233,426. Again, this is values you can find online for the Antoine's equation on graphs, or not graphs, but you can find the Antoine's equation online. And then all of that divided by 760 times the pressure, which, since it's before code, I need to actually input that. Invalid syntax. What's my, oh, I forgot my colon. I can run that. Now we want to put in the liquid feed. So that will be the mole fraction of air feed is equal to the humidity. So we had utilized the partial pressure to solve for the humidity, and we were given that the humidity is 50%. So we utilize that equation, utilize PV at the temperature of the feed, and then you'll divide that by the total pressure. And then, looks like we're all good. And we want to put in the gas flow rate for air, and that is the pressure times the molecular weight of air, which I did put air, is equal to the gas constant times, divided by the gas constant times TA feed times the velocity, which gives us the molecular flow, or the gas flow rate. So next we want to give our code some guesses for the molar fraction of the for the mole fraction of the water leaving. Since we don't have that, we need to give it an initial guess. And then we also need to have the initial guess for the temperature of the gas exiting, because we don't have the exiting temperature, we have the entering temperature right here. So we need to give it a guess, and let's make it called exit for the mole fraction of the mole fraction, and then we're going to make sure that we know that it's a guess, and then that's going to be the feed plus, no, times 10%. So we'll do that, And then we want, so next we need to estimate the temperature of the gas leaving the column. So we're going to say the temperature of the gas exiting the column is, I guess, and that is equal to the temperature of the feed of the gas. And we're just going to say 5 because we know that, we can just make an educated guess that we know that the temperature leaving the cooling tower will be higher than it is entering the cooling tower. So yes, we have that. Now, later on, we are going to need to utilize a function for the solution, and we need to utilize the none function within Python to create a open space in which we can utilize and pull from that later on. Now we're on to the actual chunk of the video. We're going to be utilizing the derivatives that we had solved previously. So first off, we're going to define a function for our derivatives, the change in the mole fraction, the change in temperature of the water, and the change in the temperature of the gas. We then need to give the definition parameters to look within the array, and we'll call that z to v. Well, it's a variable, so let's call it var. And then we want to plug in our what those are within the array. So we know that the mole fraction will be equal to the first value of the parameter within the array. And then we want to have our temperature of our water and the temperature of our gas to be at the next two. So next we need to evaluate our gas flow rate. Earlier within our function, we had, excuse me, we had called it a gas flow rate. Now, in the real life, this is actually a mixture of gas and water vapors. So we need to separate that out to be the gas flow rate for water to be equal to the mole fraction of water divided by the value. Cap lock on, number lock on. And that will be times the gas flow rate of air divided by the molecular, or times the molecular weight of air divided by the molecular weight of water. Or, got that backwards, times the molecular weight of water divided by the molecular weight of air. Solves that problem. Then we also need to call this a gas flow rate, so we need to combine those two flow rates to be water and air. Again, we'd use this as a one variable within the problem, but within real life it is a little bit messier. So now we need our total mass, or our total molecular weight, which will be equal to the gas flow rate times the gas air divided by the molecular weight of air plus the gas flow rate of water divided by the molecular weight of water. And that gives us our total molecular weight. Next, we need to solve for the heat capacity of the gas, which is equal to the heat capacity of the air times the heat capacity of water plus the heat plus the heat capacity of water in the gas phase times the gas flow rate of water. Now this is all divided by the total gas flow rate. And then we need to define our three differential equations, but in our equations we had solved for the molar flux. So our molar flux was equal to the heat transfer coefficient divided by the gas transfer, or the gas constant, divided by the temperature of the gas times the partial pressure of water, temperature of water, and minus the mole fraction at P. And that's not a capital Y. Now, we don't need to continuously haul around our molar flux. Oops. I don't have a colon. Cool. Next thing we need to do is define our three differential equations. That was the change in the mole fraction of water, and then the change in temperature of the water, and the change in temperature of the gas with respect to position. Now the mole fraction, or the mole or fraction with respect to position was equal to the specific area times the gas flow rate times the molecular weight divided by the gas flow rate times the molar flux. Then our temperature was the specific area divided by the liquid flow rate divided by the heat capacity of water, and then that was multiplied by the heat transfer coefficient, or the heat transfer times the temperature of the gas and the temperature of the water. This is our enthalpy, change in enthalpy equation that we had solved previously, and minus HV times the molar flux. Again, this is an equation we had previously solved for in the video, and we have the specific area times the heat transfer times divided by the gas flow rate divided by the heat capacity of the gas times the gas temperature minus the water temperature. Now that is all three of our differential equations. This is just so it's a little bit easier to see. Next, we want to return these values, and we need to return these values exactly the way that they were. We gave the function, otherwise it will give us the wrong values. So I need to make sure that we have, I feel like TWG isn't, let me call it the D. That's just because it's the derivative. I feel like that might get confused. So just quickly did that. Return was not. Here we go. Indentation. Didn't like the indentation. Now we actually want to converge these equations. So we will define a converge error feed. Converge error feed. Now this is for the fractions, and this we want to converge at the we want to give this array another value, and then we want to converge our values based off of the initial guesses. So this is the before we do the solve IVP, we need to convert the equation, and then we will find those variables, and then let me need to tab this over. We need to give our values our initial guesses, so it won't be guesses anymore. So it would be y exit is equal to var 2 in the first position, and then we have the tg exit var, and var is just a variable name, nothing important. Now we want to put in our IVP. So we're going to do solution is equal to solve underscore IVP. Now the IVP, we need to give it this, because that's what we want to evaluate it at. We need to give it a span, which is the height of the column. Then we need to give it the beginning of it, so that would be y height or y exit, to give it a z naught value, and then we're going to evaluate it with method dow. I can't spell method. And then we want to put the dense output to be equal to true. And then we want our and we want to put this within a solve function. So we'll put dot solve, and that will put it in an equation that we can later pull out. And then we want to return these solutions. So we want to return solve at the first position, and the last position of, or the, yes, first position, I said that right, I typed it wrong. First position of the array at minus YA feed and that's the first solution for the feed. And then we have the solution for, again, the first variable. And this gives us the answer to our molar fraction entering or exiting the feed and our gas flow rate, or our temperature of our gas exiting. And the 0 and the -1, the 0 is the first term within the array, and the -1 is the last term in the array. Now we want to subtract this from the from our guesses, not our guesses, our actual our actual feeds. Invalid syntax. So what did I didn't put a semicolon again, dude? Semicolon's eating me up. Y exit. YA. What did I not call? What did I call it? Not Y exit. Here's Y. What did I call it? I call it Y exit. Didn't like that. I don't have all the terms. I need Y exit. I need the feed of the water, feed, and I need the temperature of the gas. I named these different. I think that's what I did. I could call these TGX. Is it because these are not so again, I need to use a global solve in this function. I forgot to put that earlier. I'm surprised I didn't error out. So the global solve, I don't think that's what global solve. Now that pulls the variable solve right here, none, and it pulls it into, and we fill up that empty cell that we had originally done. Now that we're done with all of that, we need to actually do the root function to solve for the actual variable. So we will utilize the root function to give it the function, which is the converge feed up here. Converge feed. Just going to copy paste. And we need to give it our Z naught value, which will be the guesses. Our Y exit guess and our TG Y exit and our TG exit. Our null not values, and then we need to give it a we need to plug in not the exits. We need to plug in. We need to plug in the guesses, not the exits. Not comma there. Yep. All right, so I found my problem. I have accidentally typed in the molecular weight function in wrong, so it did not like that. So I previously had messed it up. It's the molar or the gas flow rate of air plus the gas flow rate of water divided by the gas flow rate of air divided by the molecular weight of air plus the gas flow rate of water divided by the molecular weight of water. So let's see if that fixes my problems. Nope. CWG not defined. I mean capital G. Man, just stupid syntax. So what? So this is my problem. I didn't give it the values. Looks like I pulled the wrong solution. There we go. All right, so now we can actually start graphing this. These values look correct. The next we want to plot out our graphs. So we want to do fig dot add, or fig equals make subplots. Then we want 3 rows, 3 graphs, and we want 1 column. Now we want to make 3 separate graphs. So we're going to do fig dot add underscore scatter. Now our x value will be equal to our z value. Then we're going to have our z plot, sorry. And then we're going to have our y value, which will be equal to our solutions within our array. So solutions, and I want this to be the first value through for all the values, and then I want to call this, this is the molar fraction, so it's going to be y. And then I want to put this in the first row and the first column. So it'll be row equals 1 and columns equals 1. Now I'm going to repeat this 3 times because we have 3 differential equations, and then I'm just going to change the values in the solutions. And this should be 0, 1, and 2. And then this one should be the water and the gas. Uh-oh, what did I do? Horns! Oops. I got too ahead of myself. I was ready to go. Can't put them all in the same spot. I still don't like that. What does it not like? Who doesn't like these? And next we want to, all right, and this is our graphs. We can make them look a little bit nicer if we want to. So we will call that figure update. And we'll make the graphs look a little bit better by shortening the width and the height is equal to, I need this to do layout. Sorry. And let's make the height 900. Alrighty. So this concludes our, well, I guess I'll explain it real quick. So as you can see, this 20 is the top of the cooling tower, and as expected, the mole fraction of the water is decreasing, or decreasing as it goes down the tube. Here we, as expected, the temperature does decrease for the water. Oh, sorry, let me rephrase that. So as it goes up the column, this is what we expected, was the temperature of the water to cool down because it is evaporating. And then for this, exactly what we expected. As the gas is rising up, it is also getting cooler as it rises up. So that concludes exam 3. It's been a ride. I appreciate Dr. Coe and allowing us to be taught so much information in a fun and easy way. So thank you so much, Professor Coe, and hope you have a great one. Thank you. Bye-bye.